All right. Hello, everyone. My name is Ian McLaughlin, and I'm a PhD in neuroscience who's wrapping up some experiments at the University of Pennsylvania. And last Sunday, I talked about an update on this novel coronavirus. And at the time, the confirmed number of cases was around 14,000. And so, as of the time that I was prepping for this Saturday night, the number of confirmed cases is around 37,000. And so Johns Hopkins Center for System Science and Engineering has kind of conveniently put up a sort of live tracker of the mapping of the coronavirus around the world. And so here's an example of what that looks like. Let's make sure that works. Yes. Okay. So the total number of fatalities now is past 800. And so according to the New York Times, output from factories that supply parts for car manufacturing is beginning to be stalled due to measures taken to limit the spread of the virus in China. And so, according to reporting by Jack Ewing, quote, every week that Chinese factories remain shuttered subtracts $26 billion from world trade, according to an estimate by Ann Boata, the head of macroeconomic research at Euler Hermes. Some of the salaries or some of those sales will be recouped after the virus subsides, but we doubt the global economy is strong enough to catch up entirely. And so the article goes on to describe how the broader supply chain would be affected by sustained repercussions of the virus in China. And, if you're interested in this topic, I suggest you check it out. And I'm only bringing this up because I think it's a great example of how biomedical science converges with many aspects of our lives. And, most of us, at least I think, are completely unaware of how tragedies like, or are completely aware of how tragedies like our loved ones suffering from a disease, directly affects our lives. And, particularly when it just kind of hits us out of nowhere. But given how interconnected all of our economies now, a significant biomedical emergency that affects one of the world's giant economies can have a severe effect on the rest of the economies. And so evaluations from the folks at the CDC, or Centers for Disease Control and Prevention here in the United States, and at the WHO, the World Health Organization, suggests, while there's still quite a bit to learn about this virus, it seems that it's fairly comparable to other coronavirus outbreaks and perhaps has a fatality rate that's lower than SARS. You might remember SARS. So what's caused this novel coronavirus to result in so many more people infected than the others historically is that this outbreak began in a large city that's kind of like a hub of transit in China. And so an unusually high, or at least comparatively higher, number of people move through there and therefore potentially exposed to people who are infected with the virus in that city. Wuhan is the city we're talking about. And so Dr. Mike Ryan, who's the head of health emergencies at the WHO, told Stat News that this novel coronavirus may go the way of SARS, which is that, due to the fairly draconian quarantines that the Chinese government's imposed, the outbreak may be sufficiently halted. But scientists at the University of Hong Kong wrote in The Lancet, and I referenced this paper last week, they write, independent self-sustaining outbreaks of this novel coronavirus in major cities globally could become inevitable because of substantial exportation of pre-symptomatic cases. So in other words, since it seems that even people who show no signs of symptoms may be able to transmit the virus, it may be particularly difficult to control for the spread of the virus. And so Dr. Amesh Adalja, who's a physician who specializes in infectious diseases at Johns Hopkins Center for Health Security, was quoted as saying, quote, "It's not too soon to talk about this. We know that respiratory viruses are especially difficult to control. And so I think it's very possible that the current outbreak ends with the virus becoming endemic." And so Sharon Begley at Stat News, which, by the way, Stat News is one of the better biomedical news outlets. So Sharon forecasts two possibilities of what we can expect from this novel coronavirus based on, quotes that she collected from infectious disease experts. And so one is it'll just progress as past coronaviruses have, like, SARS or MERS, or it begins to follow a kind of seasonal wave of spreading like the flu does. And so she quotes Stephen Morse, who's an epidemiologist at Columbia University's Mailman School of Public Health, as saying, quote, "I can imagine a scenario where this becomes a fifth endemic human coronavirus. We don't pay much attention to them because they're so mundane." And as we talked about last week, he's referring to the trends of SARS and MERS, which emerged all of a sudden but petered out fairly rapidly after infecting far fewer people than this novel coronavirus. And so Dr. Mesa Adalja, again, notes that there are 4 coronaviruses that are part of the winter-spring seasonal landscape of respiratory disease. And so 2 of them were discovered in the 1960s, but both had infected cows and bats for centuries before then. And then 2 of the others, of that total 4 that Adalja noted, had been identified that had been implicated in that early 2000s outbreak of SARS, and it also cycled between animals as well. And 2 of them had been fairly common, particularly among kids and older adults. All 4 of them together are responsible for about 1/4 of all of the sicknesses we just collectively call colds, like you caught a cold. And they all tend to cause the same types of symptoms that we recognize as colds. And so because of that, Richard Webby, who's a scientist at St. Jude's Research Hospital, a fabulous institution, who's an expert on the flu, he was quoted as saying, maybe that is the most likely end scenario if this thing becomes entrenched. So in other words, it just sort of joins the kind of portfolio of viruses to which we're all exposed, and we just kind of like call them all collectively colds. So given that researchers haven't followed these coronaviruses particularly closely, and that there have been seemingly random waves of infection by these viruses, it's possible that rates of coronavirus infections may come and go pretty unpredictably. And similar to the other major seasonal virus, the flu, the influenza virus, the consequences of infection with this novel coronavirus may also be, follow a sort of range of severity, with some very severe responses and some fairly mild, cases, and then some cases where people don't even really exhibit symptoms all that much. And between the 4 better characterized coronaviruses, there were some differences in how severe the symptoms were. And so, one of them caused more severe reactions than the others. So anyways, this is like that primary scenario that they discussed, that it'll rise and fall like past waves of novel coronaviruses. And, it'll be a story that you'll vaguely remember, like you do when it comes to SARS. The other scenario, though, was the seasonal cycle of infections with this novel coronavirus. And the reason that viruses like the one that causes the flu, again, the influenza virus, tend to follow seasonal cycles of infection is that they can't persist in high heat. And this is, of course, exacerbated by the tendency of people to aggregate in smaller spaces when it's cold out, right? You don't want to go outside as much. So Stephen Morris was quoted as saying, quote, "One scenario is that we go through a pandemic. Then, depending on what the virus does, it could quite possibly settle down into a respiratory illness that comes back seasonally." And so, as we discussed last week, viruses come in multiple shapes and sizes. Some are double-stranded DNA, some are single-stranded DNA, some are double or single-stranded RNA. And it turns out that because this novel coronavirus is single-stranded RNA, it can mutate rather rapidly. It has the potential to be able to mutate rather rapidly. However, compared to the influenza virus, which mutates quite rapidly, it has genetic features that reduce its ability to mutate quite as rapidly as the influenza virus. So as a result, Michael Farzan, who's a professor of immunology and microbiology at the Scripps Research Institute in Florida, another fabulous institution, said that, quote, that makes the mutation rate much, much lower than for flu or HIV. So then Tim Sheehan, an assistant professor in the Department of Epidemiology at the University of North Carolina, again, a great institution, he says, quote, "Everyone by the time they reach adulthood should have some immunity to the coronavirus or to some coronavirus." But it turns out that immunity to coronaviruses tends to wane as we get older. And so older adults can get reinfected despite the fact that they had already been exposed. And this seems to be the case where this group had a higher fatality resulting from SARS and MERS. In other words, older adults responded that way. And other experts highlight that we can get infected repeatedly by coronaviruses just like we can by rhinoviruses, which are the sort of the primary types of virus that we call refer to as catching a cold. So since this is the first major emergence of this particular coronavirus, it may be the case that it'll result in particularly tragic fatality statistics because it's the first time people have been exposed to it. If there are subsequent waves of the virus, it may be the case that response statistics aren't quite as bad as they were this time. Because, again, it's not capable of mutating as frequently as other seasonal viruses, and people develop enough of an immunity to limit its rapid spread. And so, I've seen scientists put it on a spectrum somewhere between the common cold, about which nobody really panics. It's inconvenient, of course, and it's dangerous for some demographics of people. But you're not up at night worrying about the cold. So somewhere between the cold and SARS. somewhat comparable to the flu. And so, we're still learning about the nuances of this virus, and so it'll just be something worth keeping an eye on as it develops. And again, this sort of tracker, which, I don't mean to portray this as like a life-threatening crisis that you need to really concern yourself with, but it is kind of handy. And you can sort of see towards the bottom here, I don't know if you can see my fingers here, you can sort of see how it's tracking the sort of rate of spread. And for a while there, it was just going straight up, but now you're seeing it's starting to kind of plateau a little bit, which is a good sign. But of course, we're relying upon, release statistics from primarily China. It's overwhelmingly present in China, or prevalent in China. And so, the accuracy of these stats may be, just something worth keeping in mind. But anyway, so this is a tool that's been put out by Johns Hopkins. So if you just like type in, coronavirus live tracking Johns Hopkins, you'll be able to find it. And it's kind of a handy tool. Anyway, so yeah, I just thought it would be worth updating on how rapidly this virus is spreading. And, again, still no reason to be super alarmed, and particularly if you're not in China, right? All right, so let's get to the topic, the primary topic for the day. And so there's a study published by a group at UCLA, or the University of California in Los Angeles, which is a university that does a lot of great biomedical research. This group has identified one potential way by which risk factors for stroke might be able to be identified via blood test. And so it's specifically testing for several proteins that circulate in the blood that may indicate a person's risk for specifically cerebral small vessel disease, called CSVD, which affects about 11 million older adults in the United States. And so cerebral small vessel disease is one of the major causes of cognitive impairment as we get older. And it results in about 1/5 of strokes in older adults. And so it's associated with kind of like overall cognitive impairment and reduced executive function. And so, when I say executive function, it's one of those phrases that's used quite a bit in cognitive neuroscience. And I suspect it's like one of those things that most people sort of intuitively understand, even outside of neuroscience, but when they hear it, right? But the details aren't necessarily particularly clear. And, one short way to put it might be, and I've heard Robert Sapolsky put it this way, executive function are the things, the features of cognition that enable you to do the harder thing rather than the easier thing, because it'll yield better outcomes than the easier thing. So to do more work to get an anticipated greater reward. But so, when that's just sort of a short way to put it. But when cognitive neuroscientists are referring to executive function, they're basically referring to the capabilities that are unique to the big and fancy Homo sapien brain. Things like inhibiting primal urges, eating ice cream or pie every time we pass by an opportunity to do so, or to do things like drink alcohol when it would just be objectively a bad decision. And so in other words, part of executive function is the decision to forego an immediate reward because we know that in the short term, it'll feel good, but in the long term, we'll be unable to accomplish a broader goal. And so, executive function also does include things like how we allocate our attention or how we concentrate. And so you should be focused on studying or working, but you compulsively keep, checking your text messages or Twitter or something. And it's that kind of moment-to-moment decision-making is also, and we refer to that as attentional control, but that's also an important part of executive function. And so, and there are a bunch of other aspects of executive function, but, it's other capabilities that you really don't consciously experience, but you probably associate with behaving maturely and prudently. And so, the things that you have to accomplish in the things you have to do to accomplish a longer term goal, deciding to ignore short-term rewards, doing work that's unrewarding in the short term, but may yield rewards in the long term, broccoli instead of Reese's peanut butter cups, right? Okay. So back to cerebral small vessel disease. So it is the leading cause of cognitive decline in these capabilities as we age. And, the allure of developing a diagnostic platform to predict whether or not somebody's at risk is that if we can identify folks who are at risk of suffering the consequences of this condition, they may be able to take action to minimize the impact of CSVD before it progresses to a point where, it's clear some damage has been done and that damage is irreparable. And so at the moment, the diagnosis of cerebral small vessel disease, CSVD, relies on brain imaging with things like MRIs or CT scans, looking for the presence of what's called high signal intensities or white matter hyperintensities. That's what they're looking for. And so just to give you an idea of what white matter hyperintensities look like. Here's an MRI from 2 people at about the same horizontal slice, meaning that if you go like from the top of the brain to the bottom and perpendicular to the body. So these are 2 80-year-old patients. And on the left, you can see comparatively like minor white matter hyperintensities, and on the right you see substantial white matter hyperintensities around the ventricles, right? And so the ventricles are those sort of like blackish, like butterfly shaped areas that are sort of right in the middle there. And then, and lastly, so white matter refers to connections between neurons. So specifically, it's the myelin that surrounds axons, which connect neurons. And so it's sort of like the rubber that surrounds the cables you use to charge your phone. And so, the problem with relying on MRI and so on, other neuroimaging to diagnose cerebral small vessel disease is that the presence of these white matter hyperintensities are thought to basically be a byproduct of irreparable damage done to white matter and axons. So, you're basically like catching a disease in mid-progression, sort of like treating somebody for measles rather than vaccinating them against it. And so what is cerebral small vessel disease? It's basically long-term, subtle damage to the blood-brain barrier due to issues with the cells that compose the blood vessels in the brain. And so just to give you an idea of what the blood-brain barrier is, the vessels in the brain are sort of unique compared to the ones in most of the rest of the body. They don't have these little openings that allow molecules to flow through, which are called fenestrations, which sort of translates to windows. And so here's a sort of cartoon that, that demonstrates the major differences between the 2 types of vessels that we're talking about. And so you can see these little sort of gaps along the surface of the vessel with fenestrations, right? That one. And it's those gaps that allow molecules to pass more freely. And it's those gaps that are basically absent in the vast majority of the brain. And so, it's sort of like a room with no windows allows no sunlight to enter. Vessels without fenestrations allow almost nothing to flow through. And, this is, by the way, like a central challenge of designing medications that target the brain, because it's really hard to get what might be ideal treatments into the brain. Because of the absence of those fenestrations. And it's also by the way, why taking a GABA supplement doesn't result in effects that are similar to Xanax or alprazolam or like gabapentin, despite the fact that those drugs target the GABAergic signaling system and even bind GABA receptors. GABA, which is the nervous system's principal neurotransmitter that reduces neuronal firing, it's inhibitory. It's unable to cross the blood-brain barrier. And, basically all the GABA in the brain has to be synthesized within the brain, from glutamate, by the way. So when it comes to what this disease looks like to people outside of science and medicine, like a whole range of things are used to diagnose the disease, which, in addition to like MRIs or CT scans, also like diagnosing the cognitive health of an individual. And so cerebral small vessel disease has been shown to be responsible for 30% of ischemic strokes. And a recent review showed that the disease, or at least, the neuroimaging that's associated with the disease, is also associated with increased risks of Alzheimer's disease. And so, that said, there's no causal link that has been made between the two. They just happen to correlate. All right, so that's basically the anatomical basis for why this study is interesting. And so, one final piece of background is that elevated levels of what are called inflammatory molecules, elevated levels of those molecules has been implicated in cerebral small vessel disease. And so you might be wondering what on earth inflammatory molecules are. And so inflammation is a very, very broad biological dynamic that basically describes how our body just responds to damage. And it includes how our immune system, blood vasculature, and biochemistry changes when we're exposed to anything from the influenza virus or the coronavirus to getting a bruise. And so it's an adaptive response that helps our body to eliminate cells that have been affected by whatever it was that damaged the body, either cells that were crushed, giving you a bruise and are therefore dying, or cells that have been infected with some kind of virus. And so, part of how inflammation occurs is via the release of molecules by cells that are either affected by being crushed, being infected, or near to the site of damage. And so some of those molecules are called interleukins. These are some of the inflammatory molecules that are released. And the interleukins are like a bunch of molecules that are part of a broader family of molecules, the name of which isn't particularly important. We've already had tons of jargon at this point, but just basically, all of these different interleukin molecules, they do slightly different things. And it's sort of like how I have trees, grass and flowers. They're all plants. They do different things. They produce different results. Some make flowers, some make fruit, but they're all plants, right? Okay, so this team at the UCLA aimed to find some of those inflammatory molecules that circulate in the blood that might be able to predict for cerebral small vessel disease, given the fact that elevated levels of these inflammatory molecules is associated with cerebral small vessel disease. And so, this effort, by the way, to identify molecules that can be measured in the blood or other, samples from the body is referred to as looking for biomarkers. And it's a major effort within both biomedical, like academic science, as well as the private sector. And so what this group did is they found a correlation between the levels of a specific selection of inflammatory molecules and the neuroimaging tests that show the presence of these white matter hyperintensities that I brought up earlier would suggest there may be some kind of relationship between the two, right? And so how did this group hone in on that specific handful of inflammatory molecules? They used a resource that, to be perfectly honest, I had no idea existed. Early on in my thesis work, using this kind of a database, this resource that they used might have very fundamentally altered the trajectory of my own project. But anyways, it's this whole database of molecules that have either been shown to or are computationally using computers predicted to interact with one another. And so, the group then scanned past research for inflammatory molecules that have been found to be associated with this disease, cerebral small vessel disease, and centered on a specific list of molecules that tended to be associated in past research. And so this group used this handy-dandy database and found that a specific molecule, a protein called interleukin 18, seemed to be the molecule that tended to interact with other molecules within the network the most. And so, in other words, past studies implicated other molecules with the disease, and they always tended to be molecules that have some kind of biological relationship with interleukin 18, that specific molecule. And so, it's sort of like if you were trying to figure out which position in football is basically always implicated in touchdowns, one study might find that wide receivers are super important. One study might show that, running backs are always involved in touchdowns. But if you were to evaluate what those two different studies had found, right, or what they had in common, what those positions had in common, it revealed that the quarterback was a pretty important part of every single touchdown scored. And whether it's a wide receiver or a running back that finishes, they both share some involvement of a quarterback. So in this case, interleukin 18 is like the quarterback. And so, again, so this group found that interleukin 18 was the most involved with all of the other molecules that were implicated in cerebral small vessel disease. And, I know it's sort of a distant metaphor, but I think it sort of holds up, the football metaphor. So anyways, this group suspected that since interleukin 18 circulates in the blood and has been associated again with cerebral small vessel disease, and they might be able to measure it and the proteins with which it interacts, the other ones within that network, in the blood of older adults who are exhibiting either normal cognition or mild cognitive impairment. And so that's what they did. So they measured the levels of these proteins in the blood of people who are around 76 years old, who either had normal cognition or mild cognitive impairment. And so, the participants in the study underwent neuroimaging to get an idea of what their brain anatomy looks like, looking for the presence of hyperintensities. And it turned out that the participants who exhibited signs of cerebral small vessel disease tended to also have higher levels of those inflammatory proteins in the blood that they'd hypothesized might predict for the disease. And so, in other words, this network of molecules, which, interleukin 18, again, was the most frequently implicated, seemed to be higher in the blood of study participants who'd shown signs of cerebral small vessel disease. And so, if a participant had higher than average levels of these inflammatory molecules, they tended to be quite a bit likelier to also exhibit signs of cerebral small vessel disease. And, a particularly compelling part of this study, though, was when they assessed people who had risk factors for the disease, things like diabetes, previous strokes, or, like high blood pressure, these inflammatory molecules were also similarly elevated. And so the group evaluated the group evaluated levels of these molecules in participants who were at just a higher risk of cerebral small vessel disease, which was a group of people who had come into the emergency room at UCLA because they were showing signs of stroke. And so it turned out that those same inflammatory molecules, once again, correlated with changes in white matter in the brain that were then later identified by MRI. And so, overall, this group may have identified a blood test that can help predict for the degree to which someone might be developing cerebral small vessel disease, or perhaps might be candidates for prevention measures to slow this or even stop potentially the progression of the disease in the first place. And so, in addition to the fact that any innovations in the development of biomarkers are like super cool and intrinsically very, very valuable, I find the study uniquely interesting because the brain regions I study, the medial habenula and the interpeduncular nucleus, tend to have very high levels of interleukin-18 either molecules or receptors for interleukin-18, which was the inflammatory molecule, again, basically that, was at the center node of this network of other inflammatory molecules that they tested for in their blood test. And so, it's not like I think these brain regions necessarily contribute to this relationship between, circulating inflammatory molecules in the blood and cerebral small vessel disease, but it's just one of those things that kind of steals my eye, particularly since the medial habenula is literally right next to one of the ventricles in the brain, dorsal third ventricle, and it's like this super weird and evolutionarily very ancient part of the brain. And well, honestly, over the years that I've been interacting with people over Twitter, I've gotten dozens of messages from folks who are either concerned that they're suffering from unusual like levels of cognitive impairment, or they're concerned that a family member is. And it's tests just like this that might help us like inch closer to knowing what we ought to do if we're at risk of developing cognitive impairment due to our unique anatomies, our unique genetics, our predispositions to something like cerebral small vessel disease. And if there's a particular diet or medication that we ought to take just because we happen to have that unique brain vasculature to stave off any age-related cognitive impairment. Another like sort of just interesting thing that I'll tack on here is that it turns out that interleukin-18, once again, levels of that molecule tend to be elevated when animals are exposed to certain drugs within, again, the medial habenula. So it's just, an interesting little thing to tack on there. Yeah, so it's efforts like these that will hopefully bring us closer to, more preventative medicine rather than just treating diseases as they crop up. And so, all right, so that's what I have for you. That's what I have for you today. So let's go ahead and start the live half. All right. Boom. Oh, let's see if I can get this to work. Hello, everyone. My name is Ian McLaughlin, and I am a PhD in neuroscience at the University of Pennsylvania. Wrapping up a couple experiments, so I'm figuring out what comes next. And so I just talked on YouTube about, let's do that, on YouTube about, well, an update on this novel coronavirus and its sort of rate of spread and so on, as well as a study that just came out that might have developed a blood test that could predict for risk factors for, age-related cognitive impairment and specifically cerebral small vessel disease, which is like one of the leading causes of cognitive impairment as we get older. And so if you're interested in that, go check it out. Type in the search bar like Ian anthropoid brain, and you'll probably get there. It's a really cool study. It's like the kind of study that could, help us get a bit closer to more preventative medicine rather than just like reactive medicine when people already have diseases. Hey, what's up, Joy? Good to see you. Camille, thank you so much for the super heart. I hope all is well with you. I also, I talked about the coronavirus, and there have been some updates on kind of its rate of spread, its comparison to other, past coronaviruses, as well as kind of putting it into a context of, what can we expect moving forward? Is this going to just, be with us for eternity as sort of like rhinoviruses are and the influenza viruses? It just sort of comes seasonally just because of how widely this novel coronavirus has already spread, mostly within China, but now outside of China. Or, is it just going to peter out, as was the case with like SARS or MERS? Okay, so you can check that out if you'd like. Can hitting your head and being in a car accident where a piece of your scalp was in the windshield? Oof, that sounds terrible. So I'm not quite sure specifically what you're asking. Wait, let's do that. But yeah, I mean, damage to, so it depends on which part of the brain you're referring to. I mean, any time where you're hitting your head that hard that skin is removed, it's probably going to have some broader repercussions. But like, for example, if you have damage in like frontal regions of the brain, in fact, I talked a little bit about executive function on YouTube just now. That is the sort of the capabilities, the kind of repertoire of capabilities that are kind of like associated with maturity and behaving prudently, that can potentially be compromised. And not that I'm suggesting that you or whomever you might be referring to is implicated this way, but it turns out that a pretty high percentage of people who are on like death row for serious crimes have had some kind of significant head trauma. I think it's something like 25% of them. It doesn't mean that, head trauma equals behaving violently, but it is sort of like executive function and inhibiting kind of more primal urges and aggression. That is part of what the frontal lobe, the frontal cortex does. And compromising its integrity can potentially compromise your ability to do those things. But that's just one region of the brain. It's a very important region of the brain, but it's just one. And, if there's damage to other parts of the brain, then you can expect other outcomes. And just because you're in a car accident doesn't mean necessarily that there's any kind of, severe damage to the brain. Okay, seeing the birth control reducing hypothalamus size paper. I have not. Oh, that's interesting. Yeah, I'm trying to remember. I feel like that's not the first paper to identify some relationship between the birth control pill and just changes in biology, like almost anatomical changes in biology. But yeah, I'll have to check that out. Disturb your part that helps you make the right decision. Yeah, right. So when we're talking about, the frontal cortex, it's like, another interesting aspect of it is as our brain is developing, from age 0 to, like 30 or 40, the prefrontal cortex, the frontal lobe, is sort of like the last brain region to kind of come online and to be, circuited in with the rest of the brain. And there are some interesting consequences of that. There are some interesting advantages as well. So that means that because this brain region takes so long to develop relative to other parts of the brain, that it is the least dominated by pure genetics. And it's the most susceptible to environmental stimuli with regards to, its development and what it'll look like, later on in life. And so what does that mean? That potentially might explain part of the reason for why adolescents, teenagers engage in kind of irrationally risky behavior. There's some dispute as to whether or not that's actually a true explanation, but that's one explanation that's been out there. And there's some interesting evolutionary advantages to that, right? Because if everybody within a tribe is only behaving prudently and with, self-interest in mind, you're not going to have people taking risks that might yield kind of substantial rewards to the rest of the tribe. And it also enables your brain to be kind of more thoroughly sculpted by your experience. And so you can adapt to circumstances that are different from, your evolutionary ancestors. So should I tell my doctor about, let's see. So is there a place I can help you with that? So should I tell my doctor? Oh, if you're talking about a car accident, absolutely. There's no good reason to avoid it. And it's just helpful to know whether or not there's any kind of, if there's any visible damage, and particularly if you're experiencing, any kind of, disruption of your kind of day-to-day activity, right? Your day-to-day capabilities, definitely. Concussion, head trauma. I think more recently we're kind of all becoming aware that this is like a non-trivial kind of injury, and it's kind of deceptively that way because you don't really see the consequences necessarily. And oftentimes the consequences don't manifest until later on in life, right? So it's like this distal relationship between the initial injury and the repercussions of that injury. So absolutely. And there are various kinds of therapy if there was a severe concussion or anything like that. If there are specific forms of therapy that are kind of devised specifically for recovery from head trauma. Can you comment on the role the brain plays in the production of anxiety and how to control it? Oh man. I could go on and on about that topic because essentially it was the topic of my PhD dissertation. So anxiety is a really interesting feature of our consciousness. I think oftentimes we kind of intuitively just kind of group it with fear, like they're essentially the same thing. And that's not the case. Actually, they function almost in opposition, believe it or not, in terms of like the kinds of behaviors that they're motivating you to engage in. Fear operates almost like at an evolutionary level. Fear operates to motivate you to withdraw yourself from a situation, right? There's somebody threatening you in a room. The fear of potential damage to yourself, or a fight or whatever, motivates you to leave, right? To flee. Anxiety, though, is slightly different. Anxiety actually motivates animals and humans to actually approach and explore, right? So this is all part of like a very like long standing framework to try and understand the sort of the times in which anxiety and fear operate similarly versus at opposition to one another. But yeah, so anxiety, you have learned that any kind of behavior, any kind of environment might be associated with something that can be bad for you, or it might not be. And so that is like the prime distinction between anxiety and fear is, fear motivates you to withdraw yourself, to remove yourself from the damage or the danger, and anxiety motivates you to explore, right? So for example, you feel anxiety like before the day of a final exam, or before walking into your boss's, talking to your boss about a promotion or something like that, or going into a job interview. You feel anxiety, but that doesn't mean that you avoid it completely and you remove yourself, right? So yes, and so how to reduce anxiety? So that is literally like a multi-billion-dollar question because like there are some good treatments for anxiety disorders, but they're actually not all that effective, and they're certainly not all that selective, right? They all have some kind of portfolio of side effects that make their effects kind of almost intolerable for some people, but less than optimal, let's say. And so what can be done? So first of all, it's important to recognize that anxiety is an important part of our daily experience. It motivates us again to engage in behavior that can be potentially beneficial. So, having some anxiety is a normal and good thing. Pathological anxiety, however, is a different story, right? That's when the circuits in the brain that generate, anxiety are, for one reason or another, hyperactive. And that can be due to past life trauma. It can arguably be due to some kind of, genetic predisposition to having heightened levels of anxiety. Oftentimes, for example, drug addictions are sort of like a byproduct of self-medicating to attenuate that kind of pathological anxiety. So of course, one thing you can do is go to a physician, go to a psychiatrist, psychologist, and, engage in some form of therapy, be it psychotherapy or pharmacological treatments, or ideally both when appropriate. Another thing that has been shown to be reasonably effective for people who have pathological levels of like high anxiety is mindfulness meditation. There was a study that came out of Johns Hopkins that showed that specifically mindfulness meditation, and specifically among people who are diagnosed with like generalized anxiety disorder, yielded, after, I can't remember, several weeks of engaging in it, yielded reduced levels of anxiety. That study also showed that it didn't like reduce levels of anxiety in people who didn't have some kind of pathologically elevated anxiety. All right. I dislike my anxiety. Well, me too. And coming from somebody who, is predisposed to high levels of anxiety, I did find mindfulness meditation to be effective, or at least helpful. There was like this course basically that was given at the University of Pennsylvania, and I found that to be very, very helpful, but there's no reason that I didn't have to pay for it. But there are tons of free resources available. I think it is super useful to have some sort of like framework, some sort of like, guided, audio kind of, whatever guidance to help you kind of figure out what you're trying to do in mindfulness meditation, because it's very unintuitive, at least for me. See a physician, check out mindfulness meditation, bunch of free resources on the net. Again, there's no reason you have to pay. You should feel the need to pay for this. Another, of course, is your sleep schedule. And I know it's sort of like, it almost seems paradoxical, because oftentimes anxiety disorders or elevated anxiety prohibits you from getting sleep, or at least makes it harder for you to fall asleep. But there's a relationship between the two. And so if you can maintain what's called like better sleep hygiene, meaning you go to bed at around the same time every night, you wake up at around the same time every day, Some people seem to be rather sensitive to the effects of poor sleep hygiene, and it can manifest in heightened levels of anxiety. Of course, another is if, evaluate your diet. If it's like totally incompetent, if it's just like you're only eating carbohydrates, try and get a little bit of fat and protein in that diet. What else? Exercise has been shown to be somewhat effective. I know for me, that's absolutely the case. Whether it's cardiovascular or resistance exercise, like lifting weights, that can be moderately effective. So those are the things to which I would look if you have, problematic anxiety. Hey, a jazzy fizzo, my nizzo. Are you worried about the effect of 5G at all? So I assume you're referring to like 5G, like the cellular network, not like 5 grams of some kind of drug. Not particularly, no. And here's why. So there have been concerns in the past that, various types of radiation might be able to interact with our biology in such a way as to produce, disruptions of our biology or produce tumors or things like that. And when I say radiation, I mean, we have a whole electromagnetic spectrum, right? The sliver of the electromagnetic spectrum with which you're the most familiar is the visible light spectrum, which is a tiny, tiny little sliver of radiation at specific wavelengths, right? And they bounce off things in the world, and then they splash up against our retina, and we have little photoreceptors that are able to be stimulated by certain wavelengths, red, green, or blue, or just yes light, no light. And those are cones or rods. And then that helps us to decipher this pattern, this distribution of photons that are splashing up against our retina. But that is just one part of the EM spectrum. Another is, for example, gamma radiation, X-rays, and Wi-Fi or Bluetooth or cellular, the cellular range. So there have been past studies, mostly, like epidemiological, correlational, statistical, and they just don't show any strong relationship. And, it's important to note that, you might be able to find a study that showed some kind of correlation, but that's just not how science works, right? We don't just look to one study and say, they found this relationship, therefore it's true. No, you have to step back and wait for, a multitude of studies to come in, and then we can scan all of them, conducted by different people using different techniques in different parts of the world, with different samples of the population, and then you can come to some sort of conclusion. And there just hasn't been any example of such a, collection of studies that have demonstrated any cause for concern when it comes to these, parts of the EM spectrum. Now, that doesn't mean that there is no effect. I mean, part of science is you wait until you see evidence, right? Show me evidence. If it's strong evidence and, it makes a strong argument, okay, I'll adjust my perspective. But as of yet, there is no such evidence out there. Okay, hey, what's up, Hal Sherman? Good to see you, man. And hello, Joy. What kind of cake? Is that what that means? Arcus Hulkin on YouTube. I'm not sure what you mean. What kind of cake instead of pie? What kind of cake? So, as Joy knows, I have very strong and devoted feelings about how bad cake is. Cake is a pestilence. It's a plague. You're always having to be forced to eat it. It's just social obligation in pastry form. Whereas pie, everybody likes pie. So stop giving cake to people, particularly at work, because then you're just like that awkward, like, yeah, okay, I'll eat this like outrageous number of calories to demonstrate to you that I care that you were born a year ago. Okay. Hello from Finland. Hello from Philadelphia. Okay. Oh, we have some callers. Okay. Did I turn up the volume? We shall see. So Kent, is that you? Are you there? Oh no, we lost him. Fortunately, we have another caller. Hopefully you'll call back in, Kent. So let's see if this... So Amy, are you there? And if so, where are you calling from? Are you there, Amy? Oh, I wonder, let me try this. Oh, volume's up. I don't know what the deal is. Oh, Amy, are you there? I think I can hear you. Are you there? Seems like there's some kind of connectivity problem. I hope you guys will be willing to call back in. Okay, what do you think of CTE? So CTE is, for anybody that's not familiar, it is a condition that refers to chronic traumatic encephalopathy. And it is a condition that sort of rose to prominence a few years ago now. And it very rapidly rose to prominence because it was kind of assessed within former professional, NFL players or football players. And there was a movie that was, a good movie about it, I think called Concussion, I think. And it's like the story of the physician who made these assessments. Okay, and basically what it refers to, as the name implies, is recurrent head trauma. So it can be subconcussive, that it doesn't cause a concussion, but it's still trauma to the head that causes, in aggregate, over a long enough period of time, these aggregations, essentially, these lesions within the brain. Interestingly, somebody who's has a background in biomedical engineering sent me a kind of compilation of some scientists and physicians who are skeptical of the validity of the evidence supporting the existence of CTE as its own condition. I've never seen any of them contend that getting head trauma is not bad for you, but they were just arguing that all of the evidence that they came about, or that they saw, was essentially exclusively correlative. And so there's some kind of contention within biomedical science as to whether or not CTE is authentically its own distinct condition. But that said, there is absolutely a relationship between, consistent recurrent head trauma, and, an increased predisposition to dementia, cognitive impairment as we get older. And so whether or not, we call it CTE or we call it something else, the fundamental concept that recurrent head trauma, disrupts our faculties later on in life, that's pretty much uncontested. So yeah. Okay. Hello. What do you think about Elon Musk's Neuralink plan to merge human brain with AI? Onurison. Interesting topic. So for anybody that's not familiar, Elon Musk is a guy who makes rockets and cars. No. Okay, everybody knows who he is, but what you might not know is that he has a company, one of his, repertoire of companies, that is called Neuralink. And the mission of Neuralink is to devise a whole brain computer interface. As far as I'm aware, their goal is not to merge the human brain with artificial intelligence. Rather, it is to basically increase the bandwidth of our ability to communicate with computers. So, make it a much smoother, synergistic relationship between the human brain and computers by devising a whole brain computer interface that's capable of interacting or recording from and stimulating enough neurons throughout the brain as to make it so that, rather than having to type or even read words, it'll just be this smooth transfer of information, back and forth. I talked about this more extensively than I will right now on my podcast called Wired to be Weird. I have 2 episodes on whole brain computer interfaces and Neuralink as the sort of like a discussion framework. But Neuralink is not the only company that's interested in developing technology like this. Excuse me. So if you're wondering what I think about that effort, I'm very excited for it. I can't wait. I think it's probably going to be inevitable. And there's no law of physics that prevents the human brain from interfacing with a computer, given the fact that our 86 billion neurons use electrochemical signaling to, communicate with one another, and computers are quite good at, receiving electrical information. Now the challenge, however, I should say, I think the whole field was pretty skeptical of Neuralink, despite the fact that on the board of directors of Neuralink are some pretty heavy hitters in neuroscience and neuroengineering, and highly regarded, highly accomplished scientists. And so it's not just like Elon Musk in his garage, developing computers. There are some real neuroscience behind it. And another interesting aspect of it is that some of the different scientists who are on the board have different technological platforms on which they've been working to develop a whole brain computer interface. So it's not like they're all in necessarily on one specific technology that may or may not succeed. One example is what they refer to as neural dust, where you would basically like decorate different parts of the brain with these tiny little receivers, essentially, these little electrodes that are able to operate wirelessly and then send information to and receive information from computers. Another is neural lace, which is this kind of meshwork of electrodes that you can inject into different parts of the brain, and it just sort of like over time naturally opens up and then is able to be sensitive to a whole collection of neurons. I should say, I guess almost a year ago now, I think, at some point in 2019, they did a kind of demonstration, like he always does, Elon Musk always does with like Tesla, right? They'd like show the big car off. They did one of those for Neuralink, and to everybody's surprise, it was much earlier than I think anybody expected. What was surprising to me, apart from, the kind of technology that they were showing, was the reaction that I saw among bioengineers and neuroengineers in particular, which was kind of surprised that was the technology that they went with, because at least a lot of them, like one example is Conrad Cording at University of Pennsylvania. He's a great neuroengineer, really nice guy too, by the way. It was just like, this is kind of older news. Like, we have more advanced technology than the one that they were demonstrating. Now I can't speak to that necessarily, but so that's what I think about it. I think, it's almost certainly going to happen. Oh, and then, one of the primary obstacles preventing us from already having this technology is that to be able to devise a whole brain computer interface, this technology is going to be able to have to interact, or it's going to have to be able to interact with a sufficient number of neurons to have a meaningful, sample of information from the brain. You don't need to record from every 86, all of the 86 billion neurons in our brain, but you do have to record from at least a sample of them to get an idea of what's going on in a person's brain, to then be able to send meaningful messages to a computer, right? And so, their estimate is somewhere in the ballpark of like 11 million neurons. It may need to be higher than that, but that's just sort of an estimate. And the problem here is that as of today, we're not able to record from anywhere remotely close to that number. And so as a result, right, like, we're going to have to make some, significant leaps, technological leaps, to be able to come even close to developing a kind of technology that's able, to accomplish their goal. And then in addition to that, just the amount of data that like recording from neurons generates is enormous, like, petabytes, like, I don't know if it'd be petabytes, but like so much, like, and just literally storing the information somewhere becomes a challenge. And then beyond that, so you have all these data, but then understanding what these data are telling you is a whole other level of complexity that we're not even close to solving. And that's why there's a lot of opportunities for people who are computer scientists or computational scientists to help, solve that problem in neuroscience. It's one of the sort of central problems of neuroengineering and, any kind of, progress towards devising a technology like this. I thought 100 billion neurons. No, so that was the estimate for a long time, is that it was 100 billion. And then, subsequent studies based, and of course, these are all like estimates. And it's not like we all have any, only 86 billion neurons. No, not one more, not one less, or one fewer. But basically what they're doing is they're taking a sample of brain, counting the neurons within that sample, and then extrapolating. It's just like you would, whatever, any kind of surface, right? You just take a sample, you characterize that sample, and then you compare, you expand the number of neurons within that sample to incorporate what would, account for the entire brain. A subsequent study did that same strategy, but with more samples of the brain, and they came to a lower number. I mean, what's a couple billion here or there, right? It's closer to like 86 billion, but, again, it's an estimate. I wouldn't base any kind of life decisions on it. Okay, thank you for the answer. I'm excited too. Do you think we can upload ourselves into a new unit after biological death? The short answer is yes. But again, with all of the caveats that I made for the whole brain computer interface and Neuralink, that we're not anywhere close to being able to accomplish that goal. But, like fundamentally, the human brain obeys the laws of physics just like computers do, right? It's just there's slightly different laws of physics that are operative at any moment in the brain than are in a computer. And so, but there's no like law that prevents us from, simulating a human brain in a computer. And so yeah. Okay, is a person born with a high IQ? Yeah, that's a really interesting and kind of controversial topic once again. What's old is new again. And so, the short answer is that there have been groups. There's research out there that suggests that a person's IQ does seem to be fairly fixed. And, depending upon when you intervene, how you intervene, levels of education very, very early on in childhood, socioeconomic status early on in childhood, and so on, it can sort of like you have a kind of window of potential higher or lower numbers. So I'm just saying there are some data that support that claim. However, a lot of that research was done years and years ago, before we had as mature of a neuroscience and genetics as we have today. And some of the more kind of nuanced research that incorporates more than just purely statistics suggests that a person's IQ number, first of all, it's not as fixed as we thought. It's influenced by more than just genetics, which is, I suspect that's what you're asking. Like, do your genes determine your IQ? And, while the broad answer to that question was for a very long time, yes. Now it's a little bit less clear because, again, the quality of research is being done by people like Elliot Tucker-Drob, whom I always bring up because I saw him give a talk. And he's a neuroscientist, but he incorporates like research techniques from other operative disciplines, right? Sociology, economics, to kind of enrich his research. And basically what he shows is that, no, it's not quite as fixed as we thought. Also, it's always worth noting that while the IQ test does measure some very important part of intelligence, unquestionably, it's measuring something important about what human intelligence does, it's not a comprehensive measure of human capacity, right? It's measuring a part of human intelligence that's important to solve certain problems. Those types of problems tend to be very important for professional attainment and, educational attainment and performance and so on. But that is not the entirety of, human potential and human intelligence. Do you think EQ is a scam, or is it as valid as IQ tests? Well, I mean, it's a useful measure, certainly, but they're measuring completely different things. And to the extent that the IQ test is, I wouldn't call it a scam, but it's taken on the sort of outsized relevance in society that it really doesn't have any business having. It's not entirely exclusive. Hey, what's up, Eleonora? Good to see you. Do some meds help your IQ? So the short answer to that, as far as I've ever seen, is no. Okay, so over the long term, so let's just take perhaps the most intuitive example, which would be medications that are used to treat ADHD. Very, very frequently abused by college students, prepping for tests, writing, essays. It's kind of a big deal these days that how prevalent the misuse of ADHD medications is. There are no data that indicate that the use of these medications actually yields long-term cognitive benefits, even performance on tests. And that, it may be the case that it's delivering the feeling that you can focus and that you're performing better. But that's not borne out in the sort of longer term results of tests and academic performance. That said, I think it is worth acknowledging that like there's a reason that these kids are using these medications, and they are quite confident that the people who I don't know if you can tell, but the baby is back from her walk, so that's not me crying in the background. She just woke up. I suspect she was asleep, and me jabbering on probably woke her up. But anyway, so there's a reason that these kids are taking these medications, misusing these medications, and it may be the case that they do improve performance, which opens us up to a whole new kind of variety of questions that are very complex and problematic. And so So, but yeah, the short answer is no. I've never seen any evidence that any drug is capable of increasing intelligence in a measurable way or IQ. All right. Obsession and overthinking. I'm not sure what you mean by that. Besides humans, what's your favorite brain to study? Well, I would be very interested to study dolphin brain, bonobo brain, and chimpanzee. I think it would be an interesting, and people do this, right? An interesting kind of domain within neuroscience to study the brains of animals that have sensory systems that are completely different from ours, like, bats, that are able to use sonar, and like, what is it like? There's actually a very famous neurophilosophy paper, I guess, or chapter book chapter called like What It's Like to Be a Bat. I think it's written by Jeffrey Nagel, I think was his name. It's been a while since I've read this neurophilosophy, but basically, the kind of premise is like imagining what the experience of an animal that has completely different sensory landscape than us is like. Yeah, I think it would be fun to use neuroscience to kind of imagine what it would be like. Oh, actually, it's something I've been meaning to talk about. There is a guy who uses computational neuroscience to project what a given landscape looks like to, for example, a bee, right? And it's really interesting. It's sort of like different colors are amplified, different colors are muted, some colors are completely absent. It would also be very, very cool to study the mantis shrimp, because they have like an extra, I think, cone that enables them to see a whole variety of wavelengths of color that are completely invisible to us. I think it'd be very interesting. Well, okay, I've given you a lot there. All right, that sounds interesting. Yeah, I think it'd be really fun. Very competitive part of neuroscience, but yeah, a lot of fun. My question was cut. What are your advices for obsession and overthinking? So this is a sort of cognitive dynamic that we refer to as either perseveration, and you can imagine what that word means, persevere. That is a kind of unique cognitive phenomenon that occurs. It's associated with a bunch of different, psychiatric conditions. For example, oftentimes people with depression ruminate over, aversive thoughts. Obsessive compulsive disorder, of course, is associated with a kind of rumination on these anxiety-inducing, considerations. If I were in the shoes of, I'm not a medical doctor. I just have my PhD in neuroscience. My perspective is that of a scientist. But what I would do is go to a physician, go to a therapist. There are people who devote their lives and have a lot of experience helping people who are ruminating to escape those sort of like cognitive loops. So that, that's what I would do. I've become like an oddly strong proponent of mindfulness meditation, like lately for some reason, but that is one of the things for which mindfulness meditation is kind of devised. Like you kind of step back from the kind of constant barrage of thoughts that bubble up from your subconscious to your consciousness. And, it's sort of like training a skill that gives you a little bit more agency as to whether or not you are going to engage a thought or avoid it. And yeah, that's my daughter in the background. She has become very, very vocal, and she has recently developed a predilection for the word this, except she says this, which is very cute. And she's very vocal. She's like this close to walking too, which means we're in trouble. Bonobos are scandalous. Yeah, bonobos are very, very cool. By the way, so for a very long time, it was thought that we were more closely genetically, evolutionarily related to chimpanzees than bonobos. And I've seen some evidence that, if we are, it's a very minor difference. And that's meaningful because chimpanzees are sort of notoriously more violent than bonobos. When two different troops of chimpanzees encounter one another, they essentially go to war and kill each other. When two troops of bonobos encounter each other, what happens is basically the females interact. This isn't always the case, but what's sort of unique among bonobos relative to chimpanzees is that the females sort of meet together and they groom one another. And they're sort of also notoriously, I guess, scandalous is what you meant. They're very promiscuous. And so they'll oftentimes solve their troop differences through sexual interaction. So it's very, completely different kind of, brain, or strategy, evolutionary strategy. And, the notion that because we're more similar to chimpanzees means we're more likely to behave like chimpanzees, that's not really necessarily supported by evolutionary biology or genetics. Okay, what is an increased reaction to emotions caused by? So when you say like an increased reaction to emotions, I'm not entirely sure what that means, right? So you're maybe like an increased emotionality, or maybe an increased empathy to the experiences of others. There is a kind of spectrum of how empathetic a person is when observing the experiences of another person, and that there are some brain correlates of that. So yes, so I mean, what would a higher emotional reactivity mean? I mean, it just means that you are so devised, right? That that is just the unique anatomy that you've inherited that predispose you to reacting in such a way, coupled with, past experiences. Did you experience some kind of trauma as a child? That can have very substantial reverberations as your brain develops. Okay. I mean, it's an interesting topic, but it's very broad, so I'm not quite sure where to go with that. So let's see. Can mixing drugs and alcohol put your brain in some form of psychosis? Absolutely. Yeah, sure. Different drugs are more or less associated with inducing psychosis, but obviously what would appear as psychosis, to somebody who had no idea somebody was under the influence of any given drug might just be somebody under the influence of psilocybin, right? And so they're experiencing psychedelic hallucinations, and that if you didn't know that they were on the drug, you might think, wow, this guy's psychotic. But, diphenhydramine, an over-the-counter medication that is used to, diphenhydramine and diphenhydramate are used as like sleep medications or as nausea medications. If you take high doses of either of them, you enter a state of delirium, and you're hallucinating, but the hallucinations are fundamentally unlike those of LSD or psilocybin or the drugs that are sort of more classically referred to as hallucinogens or certainly psychedelics. This is delirium, where you're like, instead of seeing like the walls breathing or geometric patternization that is kind of associated with psychedelics, with deliriums, you're like literally seeing people that aren't there, right? It's like complete delirium. And so, if you mix that with alcohol, sure, it would appear like psychosis. Stimulants, for a very long time, were referred to as psychotomimetics. I mean, that's sort of an old school term. I assume some people out there probably still use it, but it means that it induces a state that mimics psychosis. And as a result, for a very long time, because high doses of amphetamine induced schizophrenia-like behavior, that was one of the primary reasons for the dopamine hypothesis of schizophrenia, was that listen, if somebody takes a very, very high dose of amphetamine, they begin to experience psychosis and paranoia and some of the features of schizophrenia. And so as a result, it was for a very long time thought that, okay, so schizophrenia must arise from hyperdopaminergic states, because what these stimulants do is they elevate dopamine signaling, among other things. It turns out that that's not so much the case, but it's more complicated than that. But so I mean, high dose cocaine, high dose amphetamine will induce psychosis, and in some people who are predisposed, cannabis can induce psychosis. And so for sure. A lot of psychiatric meds are dopamine inhibitors. Yeah, that's right. Or they bind dopamine receptors that induce inhibitory effects, right? The D2 receptor, like haloperidol is like kind of a classic one. But yeah, no, you're right. And I'm not suggesting that dopamine is completely uninvolved in schizophrenia or psychosis, but it's just one component, right? I know this is one of the hardest questions in science, but why do you think we are conscious? That is one of the hardest questions in science, at least in neuroscience. And it affords us both easy response and a lack of a response. So the easy response is we're conscious because we evolved to be conscious, right? We're conscious because out of the unique, anatomy of the human brain and the complexity of the human brain, an emergent property of all of that is consciousness. And you can think of it as an evolutionary strategy, right? That humans, all of the various components that we associate with consciousness, long-term planning, self-reflection, self-realization, memory, and so on. All of those combined were part of what, evolution in the savannas of Africa happened to produce, right? We weren't super strong. And so we couldn't just rely on, being aggressive and attacking always. We weren't, super armored, we're rather vulnerable creatures. And so, we couldn't just rely on like moving slowly and having like a very, very hard, carapace or shell or something. So what we are is like an interesting combination of social complexity, socialization, being able to interact with one another and develop teamwork, and long-term stamina, right? We can just like run for long periods of time. And so, one theory is that consciousness arose because of that unique combination of evolutionary features. And so, for an organism like us to survive in the savannas of Africa, we had to be able to socially cooperate, plan for the long term, and so like because of that reliance on social cooperation, consciousness sort of naturally arose. Philadelphia from Southeast France. Hey, hello, Southeast France. Okay, so even CBD. What about kratom or coffee? So I assume, hooray for psychosis. Okay, so Idris Elba. I assume not the Idris Elba. That would be interesting to know if Idris Elba consumed CBD or kratom or coffee. I assume he does consume coffee. So when it comes to, I assume you're referring to like, do these drugs induce psychosis? So I've actually never seen any evidence that CBD itself alone extracted from cannabis, and not like, CBD, strains of cannabis that are high in CBD. Rather, CBD itself induces psychosis. In fact, there is some evidence to suggest that CBD, when also, in the presence of THC, might sort of temper the psychoactivity of THC. In other words, might reduce the kind of more psychedelic or hallucinogenic effects of THC. There's just some evidence to suggest that's the case. And then, okay, so kratom, I've certainly never seen any evidence that kratom can induce psychosis. It'd be kind of surprising if it could, just given the little bit that we know about its pharmacology, that it's primarily like opioids don't really induce psychosis unless you would consider, like irrational drug seeking behavior to be psychotic, but I would not. And so, the pharmacology of kratom is thought to be primarily centering on the mu-opioid receptor, which is the same receptor that oxycodone or hydrocodone or codeine or morphine target. But it is also thought to have some more like non-opioid effects, like monoaminergic effects, maybe serotonin or norepinephrine or dopamine itself. But I've not seen any good characterizations of the pharmacology of kratom. But if that is the case, right, stipulating that is the pharmacology of kratom, it would be kind of unusual for it to induce psychosis. But again, we don't know enough about the pharmacology to be sure about that. Coffee. So, psychomotor, coffee is a psychomotor stimulant. It has a kind of unique pharmacology relative to the others, like amphetamine or cocaine. It, does not directly target the catecholamine signaling system. So it doesn't directly elevate dopamine signaling or norepinephrine signaling. What it does is it basically prevents, it's a methylxanthine. So it prevents a neurotransmitter called adenosine from binding its receptor. And, the consequence of that is increased alertness. And the reason for that is that over the course of a day, levels of adenosine tend to accumulate. And as those levels of adenosine accumulate and bind its receptor, it kind of induces sluggishness and sleepiness. And it's kind of one of the many kind of biological clocks that are operative in the brain. And so coffee basically is like just prevents the brain from binding its adenosine and kind of tricks it into thinking, I'm not so tired. But as a result, it may be the case that some people are predisposed to responding to coffee or caffeine with psychosis. But broadly speaking, I less so than, amphetamine or even methylphenidate. Okay. Would multiple exposures to a disease be extremely deadly? I'm not quite sure what you mean by that. Like multiple exposures to a disease, like, if you're talking about like infectious diseases, like pathogens, the rhinovirus or the influenza virus, generally speaking, one of the nice things, apart from the nervous system, one of the coolest parts of the human body is the immune system. It is amazing. Like, it is so cool. There's like Darwinian selection that operates within the immune system. That is part of the reason for why you can develop an immunity to a pathogen over time. We have like both innate immunity, just cells that'll respond to anything that isn't you by attacking it. But then we also have acquired immunity, secondary immunity, B cells, T cells, that basically are like just constantly evolving in your lymph nodes. And if they're capable of binding any kind of sample of a pathogen, then they're like churned out and they're amplified. It's such a cool system. That's part of the reason for why when you feel your lymph nodes, they're swollen if you're sick oftentimes, and that's because that process is at work. And so, if you're repeatedly exposed to, the rhinovirus or influenza viruses, these are the kind of seasonal infections that people tend to associate with like winter, fall, then, you develop an immunity to it. And so that's why in some cases, some people just don't really respond all that much to a given strain of flu, whereas other people respond very heavily because they've been exposed to a strain of the flu that's similar enough that their immune system can kick into high gear much more rapidly. So, and I talked a little bit about the coronavirus today on YouTube. If you're interested, what's interesting about the coronavirus is that it seems to be the case that as we get older, even being exposed to a coronavirus, our acquired immunity tends to wane. And so that is part of the reason for why older adults are a bit more vulnerable to the severe symptoms of the coronavirus relative to like, people my age, around my age. And that, of course, very, very young children, same kind of vulnerability for a totally different reason. Oh, hello, Sun Gold Halo. Good to see you again. Would you ever recommend using ashwagandha without black pepper? So, I've tried to find I've tried to see like any good assessments of what the pharmacology of ashwagandha is, and I've just never seen any good examples. And I assume you're including black pepper in there because of, some of the studies that showed that black pepper seems to increase the permissibility of the blood-brain barrier to molecules that would be otherwise unable to cross the blood-brain barrier. So, the blood-brain barrier is a very useful thing. Like, it's there for a very good reason. Without it, we almost certainly wouldn't have been able to survive through evolution. I actually did talk a little bit about the blood-brain barrier on YouTube today. So you're interested in what on earth that is. Okay, thank you again. Why did religions emerge at some point? Is it because our brains dislike chaos, trying to find meaning and order? Okay, Onarusen, you have some really interesting topics you're bringing up. So, I'm not a theologist. My expertise is in neuroscience, and generally speaking, when you're studying any aspect of biomedical science, you are also studying evolution. And I would defer to a far greater scientist than I, Robert Sapolsky, on his approach to understanding the relationship between human consciousness and religion, right? He highlights that it plays, and I don't want to go into some of the topics that he discusses just because I think, I would prefer to like prepare to discuss those topics. So I treat it with the kind of delicacy that the topic does truly deserve. But yeah, I mean, broadly speaking, it clearly has played a pretty helpful role in human evolution over time. Okay, we've confronted the fourth wall. A lot of psychiatric meds, that's right. I feel like everybody's yelling at me, but they don't say anything. They're so mad. Well, that does sound like something that is worth bringing up with a therapist or a psychiatrist. Okay, 12 rules for life, an antidote to chaos, rules made by men. Oh, I'm not quite sure what you're referring to there. Could we make our own antibiotics at home? Not really. So antibiotics, I mean, that's a very broad category of medications. A category of medications, by the way, that's being overused and might have some pretty threatening repercussions in the not too distant future, because bacteria, just like humans, just like animals, they evolve. And, all antibiotics, broadly speaking, operate according to very similar premises, right? They attack certain components of bacteria that are common to many bacteria, right? So it doesn't matter if it's, one particular bacterium, it's vulnerable in the same way that another bacterium is vulnerable, and that's what those antibiotics are targeting. So the problem is that bacteria can evolve and become immune to those antibiotics, and that's been happening. Superbacteria, I think, is one of the terms that's used. And so, there are things that are like antiseptic, right? That, you can, sterilize your environment. That's generally speaking not necessary. And by the way, a lot of bacteria are beneficial to the human body. And, you wouldn't want to eliminate all those bacteria. Just to give you an idea of why, if you can think of your body for a second as a kind of a landscape of microbial evolution, right? And they're all competing with one another for the resources that your body generates: oil, fat, nutrients in your gut, dead skin cells, and so on, right? And that is a limited resource, just like resources are limited in the world. And as a result, there are some bacteria that either don't attack you, right? Or, they're just, you don't even know they're there. Or there's some bacteria that can generate some, benefits, particularly within the gut. But either one of those categories, the presence of those bacteria, reaping all of those resources that your body's generating, makes it so that there's not enough resources for other bacteria to come in and colonize. And so, you don't want to just rid yourself of all the bacteria in your body that's one of the main reasons you wouldn't want to do that. And so, so another, so as I was saying, like, most antibiotics are devised to target specific components of bacteria. And unless you're like an organic chemist, I would be skeptical that you'd be able to produce those kinds of things in your home environment. Okay. Will humans ever evolve beyond the illusion of free will? That's an awesome treatment of that topic. I've never heard someone bring it up that way. I don't know what you mean. Like, so, for example, I am among I think that at this point, the majority of neuroscientists who argue that there is no such thing as free will, at least in the way that most of us conceive of free will. And that it is indeed, as you're saying, an illusion. It's probably a very useful illusion, evolutionarily. But so, just because we use words like choice or decision to describe human behavior doesn't mean that we're implying that free will exists. It's just that moment of action is what we call a decision. And just because it's not, necessarily free will doesn't mean that it's not experienced as such. And so, I guess what you're suggesting would be, it's like, will something like the Kwisatz Haderach from Dune ever exist, right? Where they can sort of see, forecast future events with great accuracy, at which point you're no longer experiencing the world via the illusion of free will. I kind of doubt that. I don't know that the human brain ever has the capacity to handle that kind of magnitude of prediction. So yeah. But it's an interesting topic. At what point do you think physics and neuroscience overlap each other? All the time, constantly. I mean, certain domains within neuroscience are a little bit less concerned with physics than others, like behavioral neuroscience. But, whether you, particularly like the nitty gritty, like electrophysiology, they're literally measuring currents, changes in currents, which is like physics. Neuroscience arose as a kind of fundamentally interdisciplinary field where you had people who were, physicists, chemists, organic chemists, biochemists, behavioral scientists, all converge because all of those things are involved in human consciousness and the brain. And so, yeah, I mean, it's always a consideration. Whenever, whatever you're studying within the brain, you're always fundamentally thinking about what neurons in X, Y, or Z brain region are doing. And if you're concerned with that, you're concerned with the movement of ions and, a current. And that's all physics. Okay. Are you smarter now than before? Well, I mean, it depends on what you're referring to as smarter. There's evidence, what is it? I think it's called the Flynn effect, where it's just IQ levels, let's just, out of convenience, use the IQ test as our quantification of intelligence, stipulating all of the limitations of the IQ test, as a tool to measure human intelligence, but let's just use it as a useful tool. IQ levels have just over time have been rising. We don't know precisely why that's the case, but yes, that is a thing that's happening. Yeah, I mean, there's plenty of evidence to suggest that that's the case. Max Tegmark is one of my favorite scientists, and he talks about quantum suicide. What are your thoughts? I'm not familiar with quantum suicide. I am familiar with Max Tegmark, and I agree. He's a very compelling scientist. We put the ball to your face and shake you. What? I don't know what that means. Okay. How long should brain fog last after open heart surgery? I don't know that there's a hard and fast, expectation of how long any kind of recovery, cognitive experience of recovery would last. It shouldn't be too long. I mean, as far as I'm aware, one should recover fairly rapidly if the surgery was successful and everything, and there wasn't any kind of effect, of the anesthesia or anything like that. But yeah, I mean, if it's been more than a couple days and you're still experiencing sluggishness, you should absolutely bring it up with your physician. Are our brains physically stronger, making us smarter? No. And, the human brain hasn't really changed all that much over not only the last few generations, the last few 100,000 years. There's no reason to expect that the human brain, that my brain or yours, is altogether recognizably different from a Homo sapien in the savannas of Africa hundreds of thousands of years ago. So it's not just the neurons are getting better, right? It's, cognitive evolution, social evolution, beyond just the anatomical basis of intelligence. Are you saying black pepper is bad? No, not necessarily. No, when people are talking about combining black pepper, and I'm not 100% sure this is what this guy was referring to, or this person was referring to, but generally speaking, when people combine black pepper with, for example, loperamide. Wait, is it loperamide? Yeah, I think so. The anti-diarrhea medication. Actually, that medication happens to be an opioid. Believe it or not, it just also happens to be an opioid that doesn't cross the blood-brain barrier. It's actually a relatively potent opioid. And so, you can find stories of people who take massive doses of this diarrhea medication, and they'll claim that they get pretty substantial opioid effects. I'm not quite sure that's true. But, what is true is that, while we do have a blood-brain barrier, it's not like it's a barrier made out of steel or concrete or something. These are cells with cellular membranes. And, what we're really talking about when it comes to a barrier is that the concentration gradient has to be so high for a molecule to be able to pass through the membrane that, it just never happens naturally. When I say concentration gradient, what I mean is, if you can imagine between my hands, a spectrum of how much food coloring there is. Imagine I'm holding a tank of water and I squirt a bunch of red food coloring on this side. In that moment, there is a concentration gradient of that red food coloring, and you'll see it with your eyes, right? Be able to see it's much redder over here than it is over here. But given enough time, because of the physics of water, right, it'll diffuse, and eventually it'll diffuse down its concentration gradient, is what we call it. That molecule will tend to diffuse to areas where it has fewer of those molecules present. And so when we're talking about, taking massive doses of any given drug to get it in past the blood-brain barrier, you're doing that. You're creating such a massive concentration gradient that some of those molecules will be able to get through. When people take these medications with black pepper, what they're trying to do is, make the effect of that barrier not so significant. I think my daughter's napping now. Okay. Is it true that our ancestors are smarter than us? I've never seen any evidence to suggest that's the case, and I can't imagine why somebody would make that claim. I think it's very natural for classicism, right, to kind of respect the wisdom of our forebears. But speaking purely anatomically or socially, I just don't see any evidence for that being the case. Doesn't mean that they're less valuable than us or anything like that. We're standing on their shoulders, of course, but just because they came before us doesn't mean that they're smarter than us. Do molecules that cross the blood-brain barrier need to spend energy to cross it if they are not lipophilic? Ooh, super interesting topic. Very nitty-gritty, though. It really depends. So there are some molecules that are able to bind proteins that are present on the blood-brain barrier that essentially function as shuttles. So it's sort of if a molecule, the classic heuristic is, you can think of a receptor molecule interaction as like a lock and key, where the lock is the receptor and the key is the molecule. And if it's correctly, devised, if the structure of the molecule is compatible, let's say, with the receptor, then, and it binds the right receptor, the receptor can internalize it and shuttle it into the on the other side of the blood-brain barrier. So now, does the molecule need to generate energy? So no, I mean, I'm not aware of any molecule that itself could generate energy to, function as like a pump of some sort, right? But rather a molecule either has to be able to just cross the blood-brain barrier as it's able to cross any kind of barrier, any kind of cellular barrier, or it has to interact with some kind of, PGP pump or some kind of receptor protein that will shuttle it through the blood-brain barrier. Hashtag cross the BBB. Yeah. All right. I believe it was our forebears had less information input, therefore more time for contemplation. It's an interesting, I mean, I think there's an interesting conversation to be had there, like the effect of, how we're allocating our attention. But, I would put it back to you that like time for contemplation in the absence or in an environment of lower information exposure isn't necessarily more, isn't optimal necessarily, or isn't superior to less time contemplating in the environment of greater information. And I think, there's so much to be criticized about the effect the internet has had on our, health and our attention and our cognition and our ability to focus, for longer periods of time. But I think it's without doubt that there is a dramatic democratization of information that's occurred as a result. And so yeah, but I mean, your point is well taken. We do allocate our attention differently than our forebears did. All right. Is there a human subspecies with remarkable differences? No. So humans are Homo sapiens. And, even beyond like, you might think of, okay, so, we're all Homo sapiens, but, some of us are from different parts of the world and we look very, very different. And of course, the term that we use to describe that is race. And, I think one of the best scientists that discusses the topic of any potential relationship between biology and race is named Joseph Graves. He's at the University of North Carolina, and he approaches this from a genetics standpoint, because if there is such a thing as race, then it ought to have some anchor in biology, right? There is a biological reason that Homo sapiens are different from chimpanzees or bonobos or rhinos, right? Genetic difference. And by the way, those genetic differences are pretty subtle. Like we're very genetically similar to chimpanzees. But when it comes to race, every single time any study I've ever seen that tries to identify the kind of genetic substrate for racial differences, it always fails. And essentially what you have to do is kind of arbitrarily decide that this genetic marker is what, characterizes a race of people. And that's completely arbitrary. And it just so happens that some of the things that we use most to identify racial differences kind of have like disproportionate effects on our perception relative to any genetic differences they might indicate. So, one of the classic ones is, of course, skin color, right? Where, more melanin results in darker skin color and less in lighter skin color. But that genetic difference does not indicate, doesn't consistently indicate other genetic differences. In other words, within the continent of Africa, right? It's a very, very large continent. I think oftentimes we underestimate just how large it is. There is greater genetic diversity among all the people in Africa, all of whom have more melanin than I have, right? There's more genetic variability within just the continent of Africa than the rest of the world combined. But we would call them all black, right? And that's like, it's nutty, that we would assume that because they have this one specific phenotypic difference that they're substantially genetically different than anybody else. So no, Homo sapiens are Homo sapiens. We can all breed with one another, right? There's no being of a different race doesn't mean that you're incapable of breeding with them. That is like one of the things that distinguishes species. And so yes, this is a insofar as race is a real thing, it exclusively exists in the landscape of social of social utility, not in biology. Okay. Will future anthropologists be fascinated by the size of our thumbs due to texting? Well, I doubt it. I mean, texting for me, like I have kind of big clunky thumbs. Thanks, Dad. And it's hard for me to text with them. And so I would imagine that they would actually get smaller. But no, there's no selective pressure, right? So if you're thinking about like how evolution works, just because you have big clunky thumbs doesn't mean demonstrably, right? It doesn't mean that you're going to be less capable of reproducing, right? I have a daughter and I have these big, stupid, clunky thumbs. Okay. Let's see. Is Soma a better muscle relaxer than Flexeril? So Soma, I'm trying, I always forget. Is it Carisoprodol, I think is what Soma is. And Flexeril is like, I can't remember now. Anyways, pharmacologically, they're very, very similar. They're basically GABA B agonists. And so I've never seen any evidence that one is superior to the other. Really what you're looking at is different brands, right? It's like, is Pepsi better than Coke? Okay. I feel like I'm at a university lecture. Well, I suppose that's kind of good. I would hope that your lectures are slightly more formal than this. Man does limit has concrete number. I'm not quite sure what you mean by that. All right. Hashtag cross the blood-brain barrier. How long does it take a 2.5-year-old to forget his dad? A 2.5-year-old. Oh, I see what you're saying. I'm not sure that there's an easy response to that. Like I would imagine, just a hypothetical situation where you have, a mother and a father and let's say a boy who's born for 2.5 years. The father is present, and then for one reason or another, the father is removed from the environment. Yeah, I mean, I'm not quite sure. I mean, certainly being in the absence of a parent will have unique repercussions to, or unique effects on a given child. But I mean, I don't know that we could like quantify like how long it takes for the previous existence of this person to just kind of evaporate. I'm not sure. Yeah, it's an interesting topic, but are you related to that guy, Tom Green? Tom Green? No, I've never gotten that one. No, at least not as far as I'm aware. All right. Let's see. Cyclobenzaprine. Oh, thank you. Yeah. First memory are different for everyone, but traumatic events can stay. So yeah, that's pretty true. Like that, when you're talking about something like post-traumatic stress disorder, don't swear, my kids are in there. Please. Oh wait. So, right. So yeah, post-traumatic stress disorder arises from the sort of like the, cognitive significance, cognitive weight and valence that you're placing on this given experience, right? Like the whole purpose of, or at least one of the main purposes of memory and emotion is to, learn from your ongoing experience. And part of how we learn, part of that process is assigning emotional valence to that experience. So was this experience a positive one or an aversive one? And if it's so severely aversive that, theoretically you always want to avoid that given experience moving forward, it's so severely aversive that it was so bad for you that's why these types of memories can persist for so long and affect people pathologically for so long. All right. Can genetic traits be manufactured? I mean, the short story is yes. So that has been true for a while, but up until the inception of CRISPR-Cas9, which is a kind of a technological platform, biochemical technology that enables us to very precisely edit specific genes within any genome, such that with precision you can alter a germline gene, and as a result, and when I say germline, I mean like the genes that are present in sperm cells or egg cells, such that that person, the resulting person of the embryo that is formed by the marriage of those two things, or the coupling of those two things, their genes will be fundamentally different, and their children's genes will be fundamentally different in perpetuity. So yeah, and I mean, there's a lot of promise from CRISPR-Cas9 for the treatment of genetic diseases. In other words, diseases that arise from specific characteristics of genetics, like muscular dystrophy, for example, or Huntington's disease could potentially be like cured by those types of edits. It's worth noting, however, that like the repercussions of that kind of manipulation are very substantial, right? Very long lasting. Like, and genetics has advanced quite a bit, but we're still at the stage in genetics where we're trying to identify the functional roles that all these different genes play. But then beyond that, how they influence one another. So like there are all kinds of wacky interactions within the genome that aren't intuitive. So like, I think probably most of us are familiar with that, the role that, genes play. You have a certain code, A, T, C, or G, and then it's translated into, or transcribed into RNA and then translated into protein. But let's say you have a gene here, the presence of a gene upstream or downstream from that gene can influence how much this gene is expressed, whether it's expressed at all. They can physically interact with one another. And so, even though this gene upstream from this gene doesn't necessarily encode anything we care about, it can influence the expression of a gene about which we do care. It's a far more sensitive system than might be intuitive. But there was recently a story out of China where there was a physician scientist who I believe did his PhD or maybe his postdoc at Rice University, I believe. He got input from American scientists. So all this to say, it's not like exclusively something that happened in China. It happened in collaboration with American scientists, where this physician scientist edited, using CRISPR-Cas9, certain the genes of children that were then born. And it was sort of like for a weird reason. It was like to deal with HIV transmission. And I say weird, not that it's great that somebody that problem could be solved, but that is not a necessary solution. Like that's not the easiest nor safest way to address that problem. But anyways, yeah, he received a lot of flack for doing this. I think he was detained. I don't know if he still is. But yeah, that sent sort of shockwaves through the biomedical science community, because biomedical science is largely self-policing. And while, the folks that invented CRISPR-Cas9, notably Jennifer Doudna over at UCSF, University of California, San Francisco, she has been like integral to developing a kind of regulatory framework for the use of CRISPR-Cas9. Like, for example, it is illegal in the United States to edit anything, like germline genetics for humans. But yeah, it is fundamentally self-policing. So it's not like there's it's not like the UN would swoop in and destroy a lab that was doing that kind of work. And the reality is, once we have a better idea of what genes regulate things like height or eye color, hair color, and so on, like those things can be altered. So we're not there yet, right? Genetics hasn't advanced to that point quite yet, but it is a very real proposition. Does being left-handed have any different benefits compared to right-handedness or ambidextrousness? That's an interesting topic. I'm still trying to figure out which side will be motor dominant in my daughter. I kind of suspect that she's like me. So I write with my left hand, and my dad does this too. I write with my left hand. I do pretty much everything else, play sports and stuff, with my right hand. So it's not like true ambidexterity, but it's sort of like a species of ambidexterity. So in terms of like let's say cognitive advantages, I've never seen any like actual causative evidence showing that if you're left-handed, your Broca's area is hyperactive and therefore you're hyperverbal, right, or whatever. I guess it would actually be Wernicke's area if you're left-handed. But there are interesting correlations. Like I think left-handed people tend to die earlier, but I think Nobel laureates tend to be left-handed. There's an interesting
what is it, like a preponderance of U.S. presidents or something were left-handed. I can't remember that specific statistic, but these are just purely statistics and definitely do not indicate any causative role of motor, side dominance. But theoretically, there could be a relationship, right? So, most of the brain and most of consciousness is a byproduct of a symmetrical anatomy in the brain. We have a bilateral brain, hippocampus on this side, hippocampus on that side, amygdala, and so on. There are, however, some things that we do that are not symmetrical, asymmetrical. In fact, one of the brain regions that I study is one of the handful that is asymmetrical. And like language, for example, is largely lateralized. It is somewhat lateralized, where you have some regions in the brain that are more active, more engaged in the production of language on one hemisphere of the brain than the other. And so, theoretically, hand dominance might be able to might influence that thing. But even then, motor dominance is not necessarily a byproduct of the entire anatomy of an entire hemisphere. It's like just the primary motor cortex, supplementary motor cortex, and then peripheral nervous system stuff. And so, I wouldn't anticipate a dramatic relationship there. Okay, Mr. Know-it-all, I got a question for you. I do not know it all, believe me. Even within neuroscience, there's more that I don't know than I do. Okay. How much time of your day do you spend reading every day? A very large proportion, but not I read a lot of either biomedical news now these days. I really like stat news. I think it's one of the better journalistic outlets, specifically for biomedical science. And I have a thing, a system, it's called BiblioGo, if you're interested, that will send you kind of digests of papers that have come out. And I like to read reviews. So these are a review is not a primary research article. Oftentimes it's just sort of scan. I've written 4 of them. It scans a whole body of literature and then sort of communicates the main hits. And then if I read I follow the news pathologically closely, and I read a lot of that too. I don't read I don't read science fiction as much as I used to, which I am deeply regretting and hoping that I can solve that problem in the not too distant future. And Miss Joy is not weird. Ms. Joy is not weird. She is thoroughly normal. How dare you? Okay, how can I trick my brain to return to a normal sleep schedule? Well, that is also a multi-billion-dollar question. There are a couple things. So the first is it seems to be the case that some people are more sensitive to being exposed to a lot of blue light. So we evolved to have a circadian rhythm. We have more energy during the day, less energy during the night, and that is in part a byproduct of the Zeitgeber of the sun, the time giver of the sun, which entrains our circadian rhythm. So, and that is because when the sun is up, particularly in midday, there's much more blue light that we're exposed to than later on at night, when either the light has to travel through a lot of the atmosphere or the sun is down and there's just not much blue light. But of course, a lot of our devices, almost certainly the device you're using right now, broadcast a lot of blue light, as a proportion of the total light that it's generating. And you can download apps and stuff that will eliminate blue light. You can wear blue blockers, like I did in college, because I thought it was very cool. But yeah, so one of the things that I like to do, I'm very bad at sleeping. One of the things I like to do is as it gets later and later, I like to dim the lights more and more and more. Because we don't. I argue with my wife about this, by the way. We don't need to be living in a grocery store, but so that's one thing you could do. In some cases, having done exercise earlier on in the day can help. Yeah, Philly, woo. Let's see. Some people are quite sensitive to caffeine. And so, if you are consuming caffeine because you're tired, because you're not sleeping well, there's sort of this vicious cycle component to that. And so if you limit caffeine consumption to, no caffeine after arbitrarily pick an hour that might work for you, 3 o'clock, 12 o'clock, whatever it might be, that might help you get there. What else? It's like the fourth time I brought it up, but mindfulness meditation has been helpful for me at least. What else? Oh yeah, and then sleep hygiene. So we talked about this a little bit earlier, but some of us are rather sensitive to maintaining a kind of like coherent sleep schedule where we go to sleep at around the same time of night, and we wake up at around the same time of day. That some of us are quite vulnerable to being to having our sleep schedule disrupted if we don't do that. Okay, Queen Victoria, how does the primordial brain affect mental illness? That's a very interesting topic. So when you say primordial brain, I assume you're referring to like what people might call the lizard brain, and there's a good reason for that. Well, it's not the same as lizards, but evolutionarily there are parts of the brain that are more ancient than others. They've been in animals that predate us evolutionarily for long periods of time. In fact, I study one of those brain regions. There's every reason to assume that it's been on Earth in some animal of some sort for over 350 million years, because it's in humans, it's in other apes, it's in other mammals like dogs and cats, it's in rodents like mice and rats. And if you keep going down that evolutionary tree, you can get to fish, and some fish even have this brain region, and fish are almost as distantly related to humans as can be when it comes to animals. Okay, so some parts of the human brain are like that. They've been in animals of some sort for similarly long periods of time. However, parts of the human brain that are unique to the human brain and therefore rather evolutionarily young, novel, are the telencephalon, essentially. Like the forebrain are very, swollen neocortex. For example, we don't have as many neurons as an elephant does. An elephant has many, many more neurons than we do, but we have more neurons in our neocortex than an elephant does in their neocortex. I think it's something like 15 billion in the human brain and something like, I think, 7 billion or something like that in the elephant brain. It doesn't, the specific numbers don't matter. But so there's something about this forebrain and this neocortex that seems to be part of the secret sauce of human consciousness. However, what is it that those more primordial, more primitive parts of the brain do? So generally speaking, these brain regions, well, and by the way, like if you anatomically, you can sort of use this as a kind of handy dandy tool where the further back and down you go in the brain, the older evolutionarily speaking. And thank you so much for the super hearts. I really appreciate it. Lulu, I assume is your name. It's very generous of you. So again, newer towards the front, older towards the back and the bottom. That's not 100% always true, but generally speaking, it's sort of a good guide. And so these brain regions that are older, they tend to be more associated with subconscious processing. It's not like, if you were to imagine human consciousness as kind of like a tapestry or a painting or something that has a foreground, a midground, and a background. In the foreground of a painting is sort of like what you're paying attention to. It's the people talking to each other or, whatever it might be. In the midground, it's like, it sort of influences the ambiance and stuff. And then in the background is like, what color is the sky? Is the sun out? Are there clouds? It's just sort of like stuff that kind of broadly guides the kind of overall ambiance of the painting. It's not the main character, but it's, important for setting the stage. That's kind of like the relationship between the subconscious and the conscious awareness. It's also worth noting that the majority of our brain is involved in subconscious processing. So, the kind of classic heuristic is if you were to look at an iceberg where, what you see of the iceberg sticking out of the water is, due to physics, much, much smaller than what's under the water. And you can think of our subconscious awareness as being the submerged part of the iceberg, with our conscious awareness as just the top little part. Yes. How does it affect mental illness? That's a great topic. So first of all of those brain regions are a byproduct, like the anatomy of them, the biochemistry of them are a byproduct of inherited genes that you receive from your parents. In some cases, they're also quite influenced by life experience. And so, if you have a traumatic event as a child, that can have a regulatory effect on, subconscious brain regions or subconscious processing at least. And so, so for example, like I'll give you a reasonably concrete example. So when somebody is addicted to cigarettes or cigarettes, alcohol, or quite likely stimulants as well, they've been regularly taking these drugs, regularly smoking or drinking, their brain becomes accustomed to the chronic presence of that drug, right? And as a result, it changes the number of receptors in different brain regions. Well, it turns out that when an animal stops, let's say, smoking cigarettes, or stops ingesting nicotine, or stops ingesting alcohol, the brain region that I study, the medial lobangula and intrapedunculaire nucleus, it turns out that there's a unique pattern of activity within those brain regions. Again, evolutionary, very old, very primitive parts of the brain. A unique pattern of activity arises that seems to be very critical for the manifestation of the withdrawal symptoms that they experience. So, when somebody stops smoking, they get very agitated, very anxious. They have temperature issues with their body. They have temperature flux, cold sweats. Their appetite is all disrupted. They feel kind of cognitively sluggish. And, part of those symptoms seem to arise, in part, from unique patterns of activity within these subconscious, primitive parts of the brain. So yeah. And then generally speaking, these brain regions tend to be involved in things like emotional regulation, urges, let's see, what else? Like things like fear processing or anxiety, mood. And so as a result, definitely a lot of, mood, exactly. So like, for example, depression. It's a byproduct of a complex constellation of brain regions, but part of, one of the most important parts are a collection of nuclei, a collection of brain regions called the Raphe nuclei that synthesize a large proportion of the brain's serotonin. And so, as a result, there are some, studies, mostly in animal models, that show that, altered signaling within this brain region can be associated with depression-like behavior. There are studies that show that some of the brain regions I study tend to anatomically be different in the brains of people who have bipolar disorder, and was it bipolar disorder and I think it was depression? It might have been PTSD, but psychiatric conditions. They are pivotal in these brain regions are pivotal in promoting or regulating or increasing predispositions, reducing predispositions to psychiatric conditions. Why do we dream? To release the feelings or relieve the pain in the daily life, or what? Yeah, super interesting topic. So I have a podcast called Wired to be Weird. We talked about dreams quite a bit. That prep ended up being far more interesting than I expected. And so the short answer is we don't know precisely why we dream. However, there are some very good reasons to believe that it's probably a byproduct of a phenomenon that occurs while our brain is developing as a fetus. That after we're born, this dynamic there's no reason for it to stop. So there was no selective pressure to ensure that adults don't dream. And perhaps it quite likely plays a role in the kind of the nutritious aspects of sleeping, like, for example, consolidation of memory. Oh, thank you so much, Joy. It's very, very generous of you. Consolidation of memory. So, for example, if we have very good reason to believe that the majority of dreams occur during a phase of our sleep cycle called REM sleep, REM, rapid eye movement sleep. This is a period of sleep where patterns of brain activity tend to resemble what patterns of brain activity when we're awake look like, with some very specific exceptions. Like, for example, activity in the forebrain tends to be reduced when we're sleeping. However, when somebody's having a lucid dream, it turns out that there's like unusually high levels of activity in the forebrain. Interesting little distinction there. But yeah, so the reason that there's this connection to early brain development is it turns out that certain neurons, to connect with one another, need to engage one another with activity. They need to essentially talk to one another. So there needs to be some kind of phenomenon that induces automatic activity that cycles through the brain that will enable those connections to form. And so it might be the case. And so, if you're generating activity in the brain, things are going to happen, right? Like, it's not like, so for example, like if my eyes are closed and somebody sticks a bunch of electrodes into my occipital lobe, like visual cortex, and stimulates many of the neurons there, I'm going to have a visual experience of some sort, right? You can't like decouple those things. If somebody stimulates a certain part of my temporal lobe called the medial temporal lobe, I will experience deja vu. right? Because they're stimulating it, despite the fact that there's no reason for me to even experience deja vu. And so because there is this sort of automatic cycling of activity, perhaps as a byproduct of this developmental feature, we therefore have automatic activity in the brain, and as a byproduct, we have dreams. So they're not necessarily an indication of any kind of subconscious reality or truth or, pathology. It's just a byproduct of, what that activity looks like over the course of the day that then influences what it looks like at night. And there's a lot of other interesting aspects to this, like, the frequency of certain patterns of brain activity called PG waves. This is a unique sort of sequence of brain regions that become engaged while we're asleep. Turns out that the frequency of those waves increases if we had a particularly surprising day, if we had a new experience or were surprised by something, and those tend to be associated with dreams as well. So, do you know much about DMT? Of course, we could talk DMT. Can we finally talk anxiety? So I did talk about anxiety quite a bit. DMT, dimethyltryptamine, it is a molecule that is structurally quite similar to serotonin or other psychedelic hallucinogens like psilocybin. In fact, psilocybin is just a modified dimethyltryptamine molecule. It has a phosphate group. So because of that similarity and its resulting capability of interacting with many parts of the brain regulated by serotonin, DMT itself can interact with many parts of the brain that are regulated by serotonin. And because serotonin is one of the broadest modulatory neurotransmitters, it regulates everything from sensory experience, from cognition, from memory, from mood, libido, right? Because serotonin regulates all those things, a molecule that influences serotonin signaling will influence all of those things. Okay, what is phenethylamine? I'm not quite sure what you mean by that. Do you mean phenethylamine or phenethylamine? I'm not quite sure what you mean by that. Yeah, so what's the purpose of dreams? There isn't necessarily a purpose, right? Phenylalanine. Phenylalanine is an amino acid. Okay. So there's not necessarily a purpose of dreams. It's very likely a spandrel. It's very likely just a sort of byproduct of more critical evolutionary components of our biology, or more components of our biology that were sculpted by evolution, and it's just a resulting byproduct of that. It's not necessarily like the dream itself is nutritious in any way. It's just a byproduct of more nutritious dynamics that are occurring in our brain while we're sleeping. All right. Why do epilepsy patients have dreams during status epilepticus? So they don't necessarily. So for anybody that's not familiar, epilepsy is a seizure-associated condition where people have sort of unusual patterns of electrical activity in different parts of their brain. Depending upon where in the brain they occur, you can get different, what are called auras, or different kind of like disturbances of their consciousness or of their capabilities. For example, some people lose the ability to maintain muscle tone, so they just collapse. It's oftentimes called drop seizures. In some cases, instead of that, they just sort of all of a sudden kind of check out, they're zoned out, and they're not responsive to the environment, but they're still aware, or they're still awake and able, they don't fall. Called an absence seizure. There's, of course, tonic-clonic seizures. There's seizures where people have rhythmic contractions of muscles that they can't stop. And on and on and on. And so, there are some people who have epilepsy that arises from seizures in their medial temporal lobe that have recurrent, profound deja vu. Once again, implicating that brain region in deja vu. And so yeah, it just totally depends upon where that unusual pattern of brain activity is occurring. All right. Let's see. What time is it? Okay. Can you speak to ketamine therapy's role in remapping brain pathways in mental health disorders? Super interesting topic. So for anybody that's not familiar, ketamine is a dissociative anesthetic. So it is, I think a lot of people oftentimes they call it like a horse tranquilizer, a cat tranquilizer. And I mean, that's true, but it doesn't mean it's only good for cats or horses. It can be handy as an anesthetic because it can deprive you of consciousness while not suppressing your respiratory rhythm. So, a person doesn't die from ketamine because they stop breathing, whereas they can from morphine or fentanyl or, oxycodone, and so on. And so it has very unique pharmacologies, relative to other hallucinogens. Broadly speaking, you might call ketamine a hallucinogen at high enough doses. it is an NMDA receptor antagonist. So it interacts with the glutamate signaling system as opposed to the serotonergic signaling system, which is the one with which most hallucinogens that would be familiar interact with. And so as a result, it has unique effects. But recently, it has been shown to be helpful for people who have treatment-resistant depression. Very, very severe treatment-resistant depression. And what's interesting about it is that it can be administered, it's intravenously administered, pretty substantial doses, by an anesthesiologist, of course, in a clinical setting. But what's interesting about it is that while it does yield antidepressant effects in that moment, those antidepressant effects seem to persist long beyond just like that initial administration. And so there are, now there have been enough clinical trials, from Taiwan, hello, from Philadelphia. Enough clinical trials and studies have shown that it is effective, that the question no longer is whether ketamine might be beneficial for the treatment of depression, but why is it beneficial? And there are some theories. And in fact, the evidence is so compelling that the FDA approved an intranasal delivery of S-ketamine, which is a very similar molecule. Which is kind of crazy. It's much sooner than I expected. But one of the theories is that, so as we were talking about with those evolutionarily primitive parts of the brain, like the raphe nuclei that synthesize a lot of the brain's serotonin, a lot of glutamatergic neurons, glutamate sensitive or releasing neurons, are present in the neocortex. And the neocortex can send either excitatory, activating signals or inhibitory signals to various parts of the more primitive parts of the brain. And so it could be the case that, when you are administering ketamine and manipulating that glutamatergic signaling arriving from the neocortex, that might then result in differences in how those more primitive parts of the brain are regulated, are either excited more or inhibited more over a long period of time. That's also, by the way, a theory as to why antidepressants take so long to yield their therapeutic effects. That Prozac will elevate serotonin levels immediately, essentially. Like right when you take it, serotonin levels are high, but it takes about 2 weeks for fluoxetine and Prozac to be effective. Why is that the case? The thought is that by chronically manipulating those serotonin-related proteins, you're manipulating the way serotonin signaling occurs at baseline, or in the presence of the drug also. But you're essentially inducing a kind of a very, very subtle anatomical change in how serotonin signaling occurs. And there's sort of a similar concept behind why ketamine might be beneficial, just through a completely different neurotransmitter signaling system. But yeah, so it's quite interesting to see. What's exciting to me is not necessarily that folks with depression will have another option available, but also that finally there's a novel approach to treating depression that's being explored, rather than just another selective serotonin reuptake inhibitor, or we'll combine SSRI activity with SNRI activity. I mean, these are important innovations, but having a completely different approach can yield better results for people who for whom no medication has been effective. All right, so let's see if the call-in system works this time. Are you there? Can you hear me? Yeah. It seemed a little strange there. Okay. Why does cannabis cause depression? So it kind of depends on what you mean by that. Wait, let me see this. Yeah, so cannabis itself, I've never seen any evidence that cannabis, in a generalizable way for most people who take it, induces depression. For some people, however, there seems to be a predisposition to reacting to cannabis exposure with psychosis or mood-related psychiatric conditions, but they are a minority of people. But okay, so in those for whom cannabis can be, depression-inducing, endocannabinoid receptors are one of the widest receptors throughout the entire nervous system, both in the body and in the brain. And they regulate. It's a very, very modulatory signaling system, right? It's rarely like the main neurotransmitter at play at any given synapse. Rather, it sort of adjusts how excitable neurons are, and it adjusts how active a given synaptic connection is. And so, cannabis, therefore, well, endocannabinoids regulate everything. Again, it's a very, very broad signaling system. So appetite, all the effects that you associate with cannabis, right? Appetite, the munchies, energy levels, you get a little bit, it depends on the person. And there's a lot of pharmacogenetic diversity here. People respond to a drug like cannabis in very, very different ways oftentimes. But cannabinoids regulate everything from, again, appetite, mood, blood vessel dilation, notably in the eyes. Let's see. Oh, memory, of course, cognition, and then, of course, mood, which is one of the main reasons that people, voluntarily will take any drug, cannabis included. And so as a result, you are manipulating how these systems are functioning, and that can result for some people in a psychiatric condition. But I think it's worth noting that, relative to other drugs that people use recreationally, cannabis does seem to be considerably more benign in their long-term effects, compared to like alcohol, for example, or, tobacco. So yeah. All right, everybody, I think we should call it a day there. So thanks for tuning in. I have a podcast. It's called Wired to be Weird, and it's on iTunes and Stitcher and where you find podcasts. And I have a Patreon. If you're in a position to offer any kind of support, I would deeply appreciate it. It's patreon.com/anthropoid. But otherwise, I'm going to try and be more consistent this week. But if I fail at that mission, I will see you same time, same place, right here next Sunday. See you there. Have a great week. Okay, we'll try it this way. Yeah. Oh, this is kind of awkward. Let's see. There we go. All right. See you guys. And here. All right. See you, everybody. Oh, I just left this capillary. That's kind of dumb. All right. Thanks for watching, everybody. See you guys.